Okay, so our group did the physics of running. Now, the cool thing about running is it seems really simple, but there are actually a lot of things that go into it. The first thing that you can do when you're looking at the physics of running is analyzing the forces that are involved. So, when you're running, and if you count your body as just one object, as opposed to going down into depth with like the specific muscles and bones involved, but just your body as a whole, there's the force that you exert on the ground as you run. The ground exerts a normal force on you as well as a frictional force against your foot as you push against the ground. And then there's always gravitational force as well. So that was something that we really wanted to look into. And we did that by analyzing Davis running across the screen using the tracker program. We got a motion graph and then used that to analyze his movement using a kinematics approach. Okay, so now that we have gotten a video of Davis running across the screen, we can use the tracker program that Dr. Pepper showed us to get some information about his distance that he ran, how long he ran, velocities, things like that. So we'll define his initial starting position, his initial x, or x naught, as 0. So I've written some of our known values up on the board already. We've got his x naught is 0. According to tracker, the distance he ran over the course of that video is 3.67 meters. His initial velocity, because he's not moving, is also going to be 0. We don't yet know his final velocity, and we'll find that out in a second. And then the time that he ran during that video is 2.33 seconds. So using all that information, we can actually use the average velocity equation to find out what his final velocity would be. So the average velocity equation is the change in x, or x final minus x initial, divided by the change in time. So we can just go ahead and plug in our values. We've got 3.67 meters minus 0 meters divided by 2.33 seconds, and that gives us a final velocity of 1.57 meters per second. Now, this is important because then we can use this information to find other things. So say we want to find out how far Davis would travel if he maintained this pace for, let's say, 5 minutes, which is, if you convert it out, it's about 300 seconds. So we can go ahead and write that up here. We can change his final velocity to 1.57 meters per second. We'll change his time to 300 seconds, since we want that 5 minutes. 300 seconds. And we don't know his final x position anymore. So we'll just erase that and put a big old question mark right there. So now that we have both of his velocities, an x position, and a time, we can actually use a kinematics approach to figure out how far he would run during that time. So we'll use the kinematics equation, x equals x naught plus 1/2 v naught plus vxt. Now this is a really cool equation to use because we can actually just go ahead and plug everything in, since x is what we're looking for, and that's right at the front of the equation there, isolated on its own on one side of the equal sign. So we already know that his x naught is 0, and we know that his v naught is also 0. So then that makes our equation x equals 1/2 vxt. And then we can just plug everything in. So we've got x equals 1/2 times vx, which is 1.57 meters per second, which we just found. And then the new t value that we created, which is that 5 minutes or 300 seconds. And we converted it into seconds because that just makes everything else easier. So then from all of that, we can push through all of that, and we get 235.5 meters over time, over the course of 5 minutes. That's how far he would run. And you can tell that that's correct because our units cancel out. This seconds is on the bottom or on the denominator of our meters per second value here, our velocity value, and then we have seconds in the numerator here, and then you just are left with meters. So from that, we can also find an acceleration, which is pretty cool, also using this kinematics approach. So we can put this back into our known values. We've now got an x value of 235.5 meters. And let's say we now want to use a kinematics approach to find an acceleration over the course of 5 minutes. So we can use another kinematics equation. We'll use a difficult one this time. We'll use Vx squared equals Vx naught squared plus 2ax times the quantity x minus x naught. Now this one's a little bit tricky because we actually have to rearrange the equation. So if we rearrange that, we get Vx squared minus Vx naught squared divided by the quantity of x minus x naught, all times 1/2 is equal to ax. So from here we can plug everything in. Now that we've rearranged the equation, we've got x naught and v naught are both 0. So we are left with ax is equal to Vx squared over x times 1/2. Which again, we can just plug everything in. So we've got 1/2 times Vx, which is going to be that 1.57 meters per second squared, over x, which is that 235.5 meters we found in the last equation. Now we can multiply all this out and we get acceleration is equal to 0.00523. So his acceleration is almost constant. Now we have to worry about the units. Now when you square this quantity of 1.57, you're actually squaring both the numerator and the denominator, the meters and the seconds. So this is going to be, this numerator here is going to be 2.4649 meters squared per second squared. And when you divide that by the 235.5 meters, then one of those meters cancels out on both sides, and then you wind up with just meters per second squared, which is how we can double check that we got the proper acceleration here. So that's that.